Okay, so first, let's talk about how you can essentially do model-free learning with a model. This sounds a bit paradoxical, but it can actually work very well, and it can allow you to build very sample-efficient model-free RL algorithms where you can efficiently learn the model and then use that model to generate essentially unlimited synthetic data. If we think back to our discussion of policy gradients, one of the big weaknesses with a lot of these model-free approaches has been their high variance. And a good way to mitigate high variance is to generate more samples. Generating lots of samples in the real world is of course expensive, but if you can generate virtually unlimited samples at the cost of compute by using your model, that's maybe a lot more workable. So you could use a low variance supervised learning approach to train your model, and then a high variance policy gradient approach with as many samples as you want generated from your model. Now, when you do this, something kind of interesting comes to mind. The policy gradient is also a gradient of the total reward with respect to the policy parameters. So in a sense, the policy gradient is also computing a derivative through the dynamics. It just doesn't require knowing the functional form of the dynamics log probabilities to do this. The pathwise gradient that we discussed before in this kind of strawman model-based RL version 2.0 algorithm is computing the gradient of the same exact thing, especially if you use reparameterization trick to handle stochasticity. So in a sense, the policy gradient and the pathwise gradient should eventually give you the same thing. And in fact, they do. They're just two different ways to estimate basically the same quantity. The main difference being that the pathwise gradient requires using the derivative of the next state with respect to the current state, or the derivative of the next state with respect to the current action, whereas the policy gradient does not. So it's a different gradient estimator, potentially for the same quantity, as long as you account for stochasticity in the right way. Now, prior papers have recognized this, and they've actually studied how the policy gradient might be actually more stable if enough samples are used, because it doesn't require multiplying together lots and lots of Jacobians. So the reason that the pathwise gradient, the reason that that backpropagation method, the model-based RL version 2.0, is so difficult to use is because if you just look at the form of this gradient, you have this product over all the time steps. So it's a product of many, many matrices, and we know that if you multiply lots of matrices together, then the big eigenvalues become bigger, and the small eigenvalues, the ones less than 1, become smaller. So unless all those matrices have eigenvalues that are at 1, when you multiply them together, you're going to get a bunch of junk. You're going to get either exploding or vanishing gradients, and of course the eigenvalues are never going to be 1. Whereas the policy gradient doesn't require multiplying a lot of Jacobians together, instead it just requires you to generate samples. If you want to check out a paper that analyzes this question a little bit, I would recommend this paper called PIPP, Flexible Model-Based Policy Search Robust to the Recursive Chaos, which discusses some of the practical and numerical differences between these two gradient estimators. But if you just want to know of a practical approach, the practical approach is extremely simple. It would simply be to train your model and essentially just do exactly that model-based RL version 2.0 algorithm, only instead of using backpropagation, compute the policy gradient there using reinforce via samples generated from the model. Very, very simple, just another way to generate the gradient using the techniques we've already covered in the policy gradient lecture. Another class of methods that I'm going to discuss that use a model together with model-free algorithms is actually based on value-based methods, although it can also be adapted very easily to actor-critic methods. And these algorithms are all essentially inspired by an older technique called Dyna. And Dyna was first introduced by Richard Sutton in this paper called Integrating Architectures for Learning, Planning, and Reacting Based on Approximating Dynamic Programming. So the idea here is that you would adapt your online Q-learning algorithm to perform model-free RL with a model. And I'll first describe Dyna the way it was originally proposed, and then I'll describe sort of the broader class of what I'll call Dyna-like algorithms that essentially generalize this idea to a more powerful class of methods so that it can actually be instantiated in practice, including in the form of deep reinforcement learning algorithms. So the original Dyna method, which is not the one that's typically used today, but I want to cover this, is the following. It's going to be an iterative procedure. It's going to be an online procedure. So at any point in time, you're in some state S. you pick your action A using your exploration policy. So this might be something like epsilon greedy using your current Q function. Step 2, observe the next state S prime and the reward to get a transition SA S prime R, just like in standard online Q learning. Step 3, update your model P hat and your reward model R hat using this transition. So this you wouldn't have in online Q learning, just basically take a gradient step on your model, including the model of dynamics and your model of rewards if you don't know what the rewards are. Step 4, take a standard Q learning update. This is just like in regular online Q learning. And then step 5, this is where the fun part happens. Step 5 is where we're going to use our model to train up our Q function some more. So you can think of step 4 as basically update your Q function on the transition you just did, and now train it some more on transitions that you didn't see. So you're going to sample a state and an action from your buffer. So this is a real state that you were at and a real action that was actually taken. And then estimate the next state S prime and the reward using your model and perform an update on that. Now in the original Dyna algorithm, it actually suggests choosing the action that was actually taken in the data set, which is maybe a little bit odd because what you might actually want to do is choose the action that your new epsilon greedy policy would have taken. And that's in fact what more modern versions of this method do, but the original version works like this. So step 6 and 7 are repeated a few times, and then you take another step and collect more data. All right, so take a moment to review what's on this slide, ask any questions that you want to ask in the comments, and then we'll move on to describing the class of Dyna-like methods that are actually used in practice today. Okay, so here's the general recipe for a Dyna-like model-based RL method, which would actually be pretty good to implement in practice. And here we're going to change things up a little bit. So step 1, collect some data consisting of transitions SAS prime R. This doesn't have to be an online algorithm. You could collect multiple trajectories. Just like in that fit-a-Q iteration general algorithm that we described, there are many variants in this, and you control the rates of all these processes. So collect some data consisting of your transitions. Maybe you got these 3 trajectories. 2, use all of that data with your favorite supervised learning algorithm to learn your model P hat S prime given SA, and if you don't know the reward function, also learn R hat SA. And then we're going to repeat the following procedure k times. We're going to select some states along the trajectories that we've actually seen. So we'll sample some states from the buffer. And then we'll choose the action A at each of these states. And there are a number of choices we could make. We could follow the original Dyna recipe and just select the action that was in the buffer. Or we could select the action from our latest policy, either the greedy policy or the epsilon greedy policy. Or we could even take a random action. And there are trade-offs with all of these. If you select the action from the buffer, then you will be closer to on-policy data. You'll be closer to the in-distribution data in your data set. If you select the action from your policy, then you'll be closer to on-policy data, which might help you mitigate distributional shift in your policy, but you would incur distributional shift in your model, which might be a problem. Or you could just select an action even at random. And then you would simulate the next state S prime by using your model, and also use your reward function to predict the next state. So that's represented by these red arrows, so you can think of it as picking all the states along your trajectories and branching off from those states. And then you would train on these transitions using model-free RL. And which model-free RL algorithm you use is basically up to you. You probably don't want to use Monte Carlo policy gradients, because then you would have to make rollouts of full episode length or else truncate them. But actor-critic algorithms or Q-learning algorithms would all be fair game for this. And optionally, you can take multiple model-based steps. So here I'm visualizing the case where you just take one step from each sampled state, but you could also take multiple steps. You can take little short rollouts from each of your states in the buffer. This has a number of advantages. First, it only requires short rollouts, as few as one step from your model. Why is this an advantage? Why would we prefer to make shorter rollouts using our model instead of longer rollouts? So one reason why we might prefer to do it this way is that distributional shift accumulates over time. If you remember the dagger result, your error for a standard supervised learning algorithm that doesn't account for distributional shift scales as t squared. And even if you account for it, you still scale with t, which means the longer your rollouts are from your model, the more error they incur. The real world rollouts, of course, don't incur error because they're using the world's real dynamics. So branching off from these long real world rollouts and taking little short branching rollouts will reduce your model error, so this could be a big advantage as compared to the policy gradient approach that I mentioned before, which requires full-length rollouts right from the beginning. So using short rollouts can be a good idea. And you still see diverse states because you don't make those short rollouts from the beginning where they would all do the same thing. You take them from different states that you've actually seen in your training data. So this general recipe is a powerful recipe, and there are a number of different algorithms that have been instantiated in the literature that use some variant of this idea. So these are three algorithms, sort of sorted in order from oldest to newest that use some version of this: model-based acceleration, model-based value expansion, and model-based policy optimization. And they're all basically variants on the same thing. They're all variants on the theme where you take some action, you observe a transition, add it to your buffer, sample a mini batch from your buffer, use that mini batch to update your model, sample a batch of states from your buffer. For each of those states, you perform a model-based rollout with actions from your policy, use those transitions along those rollouts to update your queue function and maybe your actor if you have an actor-critic algorithm, and so on. So let's think a little bit about why this is a good idea and why it might be a bad idea. What are some pros and cons with these methods? Take a moment to think about it. Consider maybe writing a comment underneath with your answer. So these methods can work very well when your model is decent for short rollouts. They still rely very heavily on the real-world rollouts to actually visit interesting states. You could take the limiting case of this where your model-based rollouts are a full length, in which case you can always start them at the beginning, but typically you would use shorter rollouts branching from trajectories you've already seen in the data. This could be a bad idea in some cases because those model-based rollouts can themselves incur distributional shift, so you can't abandon real-world data collection altogether. Arguably, the states that you actually see by using this procedure are not the same as the states that you would actually see when you run your policy. So you could imagine that if you load up some states from your buffer that your new policy would never visit, and then you make a rollout using your new policy from that state, now you would end up with states that neither your old policy nor your new policy would ever produce because it's actually a mixture of the two policies. So you might end up having to train on states that you would never care about for your final policy. So there are a few pros and cons with this approach, but in general it can be a pretty good choice if you want to hybridize models and model-free learning, especially if you think that your model is really only good for shorter horizon rollouts, which learned models in very complex systems often are. Okay, so if you want to learn more about these methods, I would recommend checking out these papers that I have cited at the bottom of this slide.